Okay, second half of the unit on vectors. Let's start with the Orienteering Lab. First, you measured your pace by using your meter stick and measuring out 10 meters and counting your steps. We all downloaded a compass app on the phone and we learned how to use it. And then you had to walk 3 displacement vectors, one after the other. I'll give you 3 to practice with. Now, the goal was to walk these and then find the resultant. You wanted to find it 3 ways. Experimental, by actually walking it out and then finding the resultant by walking it and measuring it with the phone's compass. Mapping it out on a sheet of paper on a scale diagram, and then measuring the resultant with a ruler and a protractor, and then solving for it mathematically. Here's the first vector. I have my orientation drawn up here. If this is 340 degrees, that makes this angle 20, and it's 7 meters long. And I've drawn it to a scale of 1 meter is 1 inch. The second vector is 13 meters, exactly east, because it's 90 degrees compass bearings. And the last vector is 11 meters, and this is 10 degrees because it was 190 degrees compass bearings. By putting these vectors tip to tail, it makes it easier for me to see the resultant. The resultant is going from start to finish. My scale tells me it's 1 inch equals 1 meter. I measure it with a ruler. I get 10.1 inches, so it's 10.1 meters. I actually put the protractor on the board, and I get about 118 degrees compass bearings. Now, this lab was intended for people to have a chance to figure out how to add things up mathematically. Since we've already had some experience with diagonal lines and having to make right triangles out of these diagrams, some kids figured out that we could find this component and that component. And then this is its own component going across. And then find this component going down, find this component going over. Well, now we've taken these vectors that are at angles and made it a lot simpler by putting them on the north-south, east and west axes. Doing the trig, we get negative 2.39 meters for the first x component. And y1 is 6.58 meters. Now, it's going to take you a long time to do these problems unless you're good at trig. The second vector is simply x2, 13 meters, nothing for the y component. Doing the trig for this triangle, we have this component, y equals negative 10.38 meters, with an x component of negative 1.91 meters. Since we did the treasure hunt lab, most kids, I think, would realize that that's basically what we have here. We stayed on the axes. So what do you do with an x component going this way, an x component going that way, and an x component going this way? Hey, you can add them up and pay attention to those negative signs. So we get an x component of the resultant of 8.70 meters, and a y component for the resultant of negative 4.26 meters. Sometimes I don't always put the negative signs if I have an arrow to show me my direction. But if you don't have an arrow to show the direction, if you're going to use a data table, you got to have the negative sign so you can keep track of which way you're going. And everybody knows that we have a right triangle. We use the Pythagorean theorem, and we get 9.68 meters. Doing inverse tangent, you get 64 degrees for this angle, which will make that angle 116 degrees. And that's compass bearings. Let's take a look at our answers. Mathematically, we have 9.68 meters, 116 degrees compass bearings. Look how close we are to our graphical method. They really do reinforce each other. I think we did this right. In the experiment, I would expect to see more error because it's hard to actually walk these things and look at your phone and try to get a good angle. Let's have a couple examples of velocity vectors. Let's say we have a boat and it's in water that's not moving. Well, maybe it's got a velocity of 5 meters per second. That's how fast it can move through the water. But what if there was a current in the water? What if this was a river and the boat is going upstream, but the river is moving backwards, going downstream? What would happen to the boat? We could put these vectors tip to tail to find the resultant. First, we put the velocity of the boat, and then the velocity of the river, and we can see that we have a resultant of 3 meters per second. And what would happen if the boat went downstream with the current? Again, we can put them tip to tail to see a resultant. Now the boat will be going 7 meters per second. Well, we would say that's relative to the land. It's still pushing 5 meters per second through the water. But when you add the velocity of the water, the boat now travels faster relative to the shore. Now the boat is going to try to cross the river. But remember, the current is going downstream. That gives us a speed of 5.39 meters per second with an angle of 21.8 degrees south of east. Now keep in mind that the boat really doesn't go forward and then the water brings it down. It's both happening at the same time, which is why it's common to see these vectors drawn tail to tail. While the boat is heading this way, the current is bringing it down, and the combined motion actually makes the boat move like this. Some kids think the boat is going to end up angling like this. It doesn't. The motor of the boat is trying to make it go forward while the current brings it down, and it stays in this orientation as it comes down like that. If you draw the vectors tail to tail, it's still the same resultant. Having trouble visualizing this? Put them tip to tail. Makes it easier to see. But what if the boat needed to cross the river straight across? It wouldn't be allowed to drift downstream because there might be a dock over here that it has to get to. Which way should the boat head? Well, if the current is going down at 2 meters per second, that boat is going to have to angle upstream to keep itself from drifting down. Well, the speed of the boat through the water is still 5 meters per second. That's how fast it can push through the water. So the boat is trying to do this while the current is bringing it down. And yeah, that'll be the resultant. It'll end up going sideways. Well, to visualize this a little bit better, we'll put the two vectors tip to tail, the boat, the current, and then that'll be the resultant. I know people think it's weird that the resultant is along the x-axis, but it's the one vector that replaces these two. Using the 2 and the 5, that's the hypotenuse, we get 23.6 degrees. That's how much the boat would have to angle up to fight the current to maintain the easterly direction and go straight across. The resultant speed is actually smaller than how fast the boat can push through the water, because some of this boat's effort is going into fighting that current, bringing it down. Leaving these vectors tail to tail, we could actually look at this another way. We can break the boat's vector up into two components. What do you think that y component would have to be so it doesn't drift downstream? It would have to be equal to the current. We would make it 2 meters per second. So you could solve for this angle by taking that y component and bringing it over here. It's really going to be the same thing. And when I break a vector up into its components, I don't need that vector anymore. I'll just look at the components. Well, we can see that the river's current vector is going to cancel with the y component, leaving us with the x component as the resultant. That's the only thing left. That's what's going to happen. Well, to get more practice, you can certainly read the chapter notes, do the problem sets, which have answer keys in those chapter notes, but be aware that some of those problems are hard. We haven't done all the hard ones yet. Watch these videos, go over your lab diagrams, and go to the spreadsheet where we all put our data for the Orienteering Lab. There's lots of problems right there. Everybody did different values, and you can check your work, try a problem, see if you get their answer. And please do at least a problem a day. every day, Saturday and Sunday. You can't take a day off. You'll get rusty. When you really study, yeah, you should put in at least a half an hour, but plenty of other times, hey, give me 10 minutes a day at least.